Right now, tonight, the moon is moving away from you. Not drifting, not wandering, retreating at 3.8 centimeters a year, measurably, verifiably, and it has been pulling away since long before there was anything alive on this planet to notice, though not always at the rate it is going now. That number sounds trivial, a thumbnail's width. But run it backwards over billions of years, and the moon was not out there where it hangs tonight. It was somewhere else entirely, somewhere much closer, and the sky looked nothing like what you have ever seen. The question is what that meant for us then, and what its leaving means for us now. To understand why it is leaving, you have to understand where it came from, and the answer is violent. About 4.5 billion years ago, the leading explanation is that a body roughly the size of Mars, which planetary scientists call Theia, struck the young Earth at an oblique angle. Not a glancing blow, not a near miss. An impact that partly melted both bodies, ejected an enormous cloud of vaporized rock into orbit, and left that debris to coalesce, within what we think was a geologically short time, into the moon. It formed close, catastrophically close. And the distance between Earth and moon has been opening ever since. How close is close? Models of the aftermath put the newly formed moon just outside the distance where Earth's tides would have pulled it apart. Only a few Earth radii out, against roughly 60 Earth radii today, and creeping outward from there ever since. Put that early moon in the sky, and it would have loomed many times wider than the disk you know, a swollen presence covering an enormous arc of it. And because it was so much nearer, the gravitational grip it exerted on the oceans was dramatically stronger. The tides it raised were not the meter-scale tides of a modern coastline. They were walls of water, hundreds of meters high in some estimates, surging across a planet that was itself spinning far faster than it does today. Though how much faster leads somewhere, the numbers have not yet settled. We can actually read how fast the planet was spinning, not from theory, but from fossils. Ancient corals lay down daily growth rings, and those rings tell us how many days fit inside a year. And since the year itself, Earth's orbit around the Sun, has not changed substantially, the ring count tells us how long a day was. Devonian coral from roughly 400 million years ago indicates a day of about 21.9 hours, approximately 2 hours shorter than today's 24 hours. 2 hours sounds modest until you realize that is just 400 million years of slowing. That rate has not held steady. It shifts as the continents move and the oceans reshape the tides, but run the mechanism backward rather than the number, and you still arrive at an early Earth turning through a day measured in hours. Not the comfortable cycle you have never had cause to question. The mechanism connecting those two things, the moon retreating outward while the Earth spins slower, is tidal friction. The moon's gravity pulls a bulge in Earth's oceans. Because Earth rotates faster than the moon orbits, that bulge is dragged slightly ahead of the moon's position. The bulge pulls the moon forward in its orbit, which pushes the moon into a higher, wider orbit, farther away. In return, the drag on Earth's rotation bleeds away angular momentum, lengthening the day. The moon's retreat and our longer days are not two separate phenomena. They are one transaction, still ongoing, and we are still paying for it, though the cost is almost invisible until you look at what it has already done to the moon itself. The same tidal mechanism that slows Earth's spin once worked on the moon's rotation too, and it ran to completion long ago. Early in the moon's history, Earth's tidal grip slowed the moon's spin until it matched its orbital period exactly, once around Earth, once on its axis, locking one face toward us. Near enough, anyway. A slight wobble in the orbit lets us creep around the edges, and see about 59% of the surface over time, but the rest never turns our way at all. The far side was structurally invisible to every human who had ever lived until a Soviet probe called Luna 3 photographed it in 1959. What it showed was startling. The near side is dotted with vast dark plains of ancient volcanic rock called Maria. The far side has almost none. The moon is not symmetrical, and that asymmetry carries its own questions. But before those questions, the record the moon has been keeping in that locked Earth-facing hemisphere is stranger still. The moon, having no plate tectonics and almost no geological activity to speak of, preserves its surface in a way Earth cannot. Some of the rocks returned by the Apollo mission's clock in at over 4 billion years old, older than almost any surface rock you can find on Earth. The craters at the lunar poles that have not seen sunlight for billions of years hold water ice, trapped and stable in that permanent shadow. And the surface itself, ground down over aeons by micrometeorite impacts under a hard vacuum, has become a layer of fine glass dust, regolith, that swings between roughly 127 degrees Celsius in sunlight and about minus 173 degrees Celsius in shadow. The moon is an archive, but it is not a static one. And to know how we know its distance with the precision we do, you have to know what was left behind on it. The Apollo missions placed corner cube laser reflectors on the lunar surface, arrays of prisms engineered to bounce light directly back to its source. Observatories on Earth fire laser pulses at those reflectors and time the return to within fractions of a nanosecond. The distance falls out of the arithmetic. The measurement is not inferred from models or extrapolated from theory. It is taken directly, year after year. And it is from those measurements that we know the 3.8 centimeter figure is an average drawn from decades of those returns, varying a little from year to year, and that it is what is happening right now, which means something we treat as a fixed feature of the sky is, on any time scale worth thinking about, a temporary one. Stand on Earth and look at a total solar eclipse. The moon, 3,474 kilometers across, 384,000 kilometers away, covers the sun's disk almost exactly. The sun is about 400 times wider than the moon, and it is about 400 times farther away. That ratio is, to a striking degree of precision, what places us at the moment in cosmic history where the two objects appear nearly the same angular size from Earth's surface. Other moons do pass in front of their sun. The Galilean moons throw real shadows across Jupiter, while Phobos is too small to do more than cross the sun's face from Mars. But that near-exact angular match, that coincidence of apparent size that produces totality with its corona blazing around a perfect black circle, is not a common feature of the solar system. It is specific to us, and it is specific to now. And now is temporary. As the moon retreats, its apparent size in the sky shrinks. We are already past the point of perfect coincidence. The moon's orbit is slightly elliptical, and at its farthest point today, it already fails to cover the sun completely, producing what astronomers call an annular eclipse, a ring of sunlight around the dark disk, which is beautiful in its own right, but is not totality. The window in which a perfect total eclipse is even possible is narrowing. It will not close tomorrow. It will not close in a century. But it will close, not as a theoretical limit, but as a calculable date, receding from us on the same schedule as the moon itself. When that window closes, it will close permanently. There is no mechanism that reverses the moon's retreat on any time scale relevant to life on this planet. The last total solar eclipse visible from Earth will happen on a day with weather, with a landscape underneath it, possibly with nothing that can appreciate what it is watching. The corona will flare out around a disk that only just manages to cover the sun, and every eclipse after it will leave a thin ring of sunlight the moon can no longer hide, so that after billions of years in which that precise geometry was available to anything with eyes, it will not be available anymore. No record will be made. No one will have been told this was the last one, because there is no way to announce it in advance to the right audience. So here is where the thread closes. The moon formed in catastrophe, close enough to raise tides that reshaped a planet, and it has been moving away ever since, slowing our days, locking its own face toward us, preserving in its craters and its regolith a record of conditions that no longer exist anywhere accessible on Earth. It is moving away right now, measured in the travel time of a laser pulse. And the thing we lose when it goes far enough is not the moon itself, which will still be there, still enormous, still governing tides. What we lose is the accident. The one brief era in the history of this system when the moon and the sun appeared, from this surface, to be almost exactly the same size. That is what a total eclipse is, and that is what is leaving.